Yeah, thank you very much. Um, yes, I'm going to give an update of the Svelvik C2 Field Lab. I guess many have probably heard about Svelvik. So it's a field lab that's located about 1 hour kind of south of Oslo in the Drammensfjord. And uh, so, so the field lab is located here. So this is in Peninsula in the Drammensfjord, and this is an active sand quarry. So the field lab was was created as a quantification lab um, to um, uh, to develop and test methods for the quantitative monitoring of CO2 storage, in particular the quantification of pressure and saturation and how to distinguish between them. Um, the It's fast, it's cost efficient, and it allows repeatable experiments. And what that means is we can do a complete C2 injection experiment in a week. It's cost efficient because it's short, but it's quite shallow. That means we don't need any complicated equipment. And repeatable, so we have done, I think, 7 or 8 CO2 injection experiments, and we see the same behavior of the C2 every time. And that means when we do an experiment, we know exactly what to expect. We can optimize the planning to have the best results. And then also, after 2 months, the CO2 is gone, and we can start from scratch. Okay. So we have thing. Yeah. So we can inject kind of water or CO2 in injection well here. If we inject water, we only affect the pressure. If we inject CO2, then affect pressure and saturation. But when we stop the injection, then the pressure goes down to the background level really quickly, and we only see the saturation effect. So we have one monitoring well where we can inject in 65 meters, and we have four injection well, and we have 4 monitoring wells. And each of these monitoring wells are quite heavily instrumented behind the casing. So we have fiber optic cables, DAS, DTS, and DSS. We have electrodes, 16 per well for EAT, with pressure and temperature sensors in 3 of the 4 monitoring wells. We have capillaries, and we have straight and helical kind of DAS cables. Yes. So the fiber optic cables are organized in a loop. So they start and end here at the instrument cabin at this patch panel, and there, so they go out and go down in the wells from one to the other, and we can combine them at the patch panel as we want to have some flexible loops. What's new is that we also now have fibers in the injection well. And we also have attached some kind of surface fibers. That was so far only project-based, so they're not there anymore. But it's an ongoing project, so we are installing some at the moment as we speak. Okay, so what happens when we inject CO2? So what's shown here is 2 sections. So this is depth, meters or 80 meters. So this section A from M4 to M3, and the section B from M3 to M2. When we inject CO2 here, it doesn't stay at the steps, but migrates upwards quite quickly. We do have a mud layer that actually has a seal, so we have an accumulation of CO2 around M3. When you look at what's the extent of the CO2 plume, so we know this quite well because we have the data at these 3 lines from the crosswell. We also have the VSP survey here, so we know exactly how that looks like, but we don't know what's the extent there. Also, when we inject after 3 days, the plume is fully built up, but when we inject further at the same rate, we have a steady state, so the plume doesn't change. But it also means that the CO2 that goes in kind of one side has to go out somewhere else, and the assumption was that it comes out here. Then there was a test done by Ressmann, who tested a highly sensitive tracer that they injected with a C2. And the biggest result, or the biggest signal, was here the injection wall. So we knew that. Then we found out that there's some C2 leakage here where the plume is. We did not know that. And then there's some C2 leakage and suspected that it would be. So we do a lot of seismic measurements at the site. This is for developing and testing different methods. So we have really good repeatability. So this is an example that we call 1D4D. So we have one source in place and we just leave it there. And then we have hydrophones or we use DAS in the wells. And this is from two different rate paths. So the one through the seal where there's no CO2, and this is 5 days, and we see there's no change in the waveforms, and there's also no change in the spectrum. When we look at the one that goes through the kind of upper part of the CO2 plume, we see that's only very little change in the amplitudes here until the CO2 until the CO2 rushes in, and then we have the plume, so we have a lot of attenuation. We also have the delay here, and we see that very clearly in the spectrum also exactly when things happen. So that's very nice. And the seismic measurements serve either to produce data if we want to test some algorithms or some new methods, or as a kind of reference for non-seismic methods. Yes. So we also have leakage. That's how we knew that there was some CO2 to be kind of expected here at the injection well. So the CO2 is coming in here. Some of it or most of it is going to the plume, but about 10% is coming out here on the outside of the injection well casing. And we know that, so the two casings and the outer one goes to 26 meters. So we know that what comes out here has to travel here on the outside of the injection well. It's not quite clear if it just goes up straight or if it goes to the plume first and then flows back. But so the kind of uppermost 26 meters, we are quite sure. And that's just some examples from how it looks like when we try to detect gas bubbles using DAS. And we had some pulse CO2 injection here, and we saw that we can actually track the CO2 bubbles coming up. It was quite nice. So we come to the upgrade part. So this is how the CO2 field lab looked in 2019. That's how it looks today, or at least last week. So the kind of yellow part is the same. We have some more containers here, and we have two more wells. One is a perforated wells going down to 80 meters, which is perforated top to bottom to allow hydraulic conductivity, and also to allow to use kind of electrical and magnetic measurements on the inside. And then we have a shallow source well where we can install surface source, so sparker in about 3 meters depth, so it's still surface, but it's not affected by any surface changes due to kind of weather or groundwater changes. Yes. We're also planning an update of Svelvik 1, which used to be the exploration well. We have a casing down to 200 meters. At the moment, it's filled to 88 meters with sand. We want to install, so first we want to remove all the sand, then install a steel casing, install some plugs, kind of do some cementations, but have different materials kind of in the annulus. We're thinking about creating defects in the steel casing. I mean, no holes, but making it thinner to simulate kind of corrosion effects. And we also want to inject, first of all, through both casings in the formation at 100 meters depth, and also to inject in the annulus. That means we can simulate leakage behind the casing. Okay. Site usage. So we have so this is how many injection campaigns in blue and how many projects were at the site since 2019 to 2025. Okay, thanks. And in the first year was good. Then we had Corona. That was a little bit less activity. And then it went really off the last couple of years. So we have everything from CO2 monitoring, leakage detection, well integrity, quite a lot of dust, even drones. And the data from the site, the 4D data, are quite useful for testing FWI, RTM, dust processing, and others. We had a lot of projects there, which were supported by GeoEnquire with groups from Germany, Italy, and the US. And we have also some plans this year. I mentioned legacy well upgrade. We are going to inject some dissolved CO2, and we also have one more GeoEnquire project. So this is an example for using tube waves. So we have a VSP line. We took one kind of shot point here. This is the wave down going in the world, so it's 30 meters or here, 60 meters there. And we see for the baseline, this is quite straight. And when the CO2 is in there, we see a small kink here in the first arrival. But we also see these tube waves, which are an effect of the CO2 changing the properties of the material behind the casing. We had a nice project at the site a couple of years ago, where the question was, can we use cosmic muons for CO2 monitoring? The answer is yes. And that was actually the first test using muons for CO2 monitoring worldwide. This is something that's going on right now and will continue mostly in August, September. This is a small British company, a startup that had the idea to actually inject dissolved CO2, similar as you do in basalt. But in this case, the idea is not that the CO2 should be kind of mineralized, but it should just stay dissolved. So the advantage of this, you don't need great depths, you don't need a cap rock, and you can do it really anywhere, which is a really nice idea. What they're going to be doing is they will test their kind of mixing equipment in injection well, and then try to demonstrate on a small scale that it works and that the CO2 stays in solution. To sum up, so the field lab is there for controlled testing of new technologies, of CO2 monitoring and well integrity. It's fast and repeatable. We have different monitoring scenarios, different things that can be tested. We have a very excellent data quality and repeatability, and also data available on CO2 data share. And the data I'm talking about are the ones from the 2019 experiment that are behind these kind of images. And also, it's an Excel facility, so there's open access. Yeah. Thank you very much.